So let me start today's lecture. So this is the fourth lecture of my advanced nuclear physics course. And throughout my lecture, I'm introducing microscopic mean field approaches for nuclear many-body problems. And today, I will explain Tamm-Dancoff approximation and random phase approximations to describe collective excitations of atomic nuclei. So again, this is just a syllabus. And okay, so in the first lecture, I just gave you some overview of modern nuclear physics. And in the second lecture, I introduced the so-called Hartree-Fock theory and the density function theory. And those are very closely related, especially in nuclear physics case, since we use effective interaction. The Hartree-Fock theory can be regarded as kind of density function theory. And then on top of the Hartree-Fock theory, or you may say density function theory, we are trying to develop some more correlations or some theoretical framework to describe phenomena which is not accessible by Hartree-Fock method. So first one was the pairing correlation. And last time I introduced the BCS, Bardeen-Cooper-Schrieffer theory, and I introduced a bit about HFE, Hartree-Fock-Bogoliubov theory. Okay, and this time I will introduce how to describe collective excitations. So this is the excited state, so not the ground state. So we need some description for the excitation modes. And okay, so this lecture and the last lecture was, it will be some detailed derivations. But after that, the remaining lecture will be some kind of applications. So please be patient. Okay, so now today I will introduce what is collective excitations and explain how to describe this. Okay, the purpose of today's lecture are following. So first one is to introduce the essence of what we call collective excitations for atomic nuclei. So it cannot be explained just as single particle excitations, but based on TDA, Tamm-Dancoff approximation, or RPA, we can understand what is the origin of this collective state. And I will explain what are TDA and RPA and clarify difference between them. So TDA is more simple approach, and RPA is extension of TDA. Okay. So, and the main purpose will be to understand how collective excitations are described or can be understood within the microscopic mean field approaches. This is the purpose. Okay. So let me start with explanation a bit about the shell model. So I introduced some mean field or one body potential can explain the emergence of nuclear closed shell, the so-called magic numbers, 2, 8, 20, 28, 50, 82, 126, and so on. And I will explain a bit about this and how can we understand excitation spectra based on the shell model. So it works pretty well to explain some part of excitation spectra. Okay, so here I just show some typical example. So this figure shows some low-lying states around lead-208. So the central one is lead-208. Lead-208 has doubly closed shell. So magic number, proton magic number 82 and neutron magic number 126. And those are neighboring nuclei with one one particle or one hole. It means one protons are added to the closed shell 82, or one neutron is added to the closed shell 126, like this. And those are excitation spectra. So we take 0 as a ground state energy. Okay. So as you can see, for instance, lead weight has doubly closed shell structure. So it has closed shell, so it is difficult to excite nucleon because of the shell gap. So as you can see, there are no low-lying energy, excited states here in case of lead weight. Okay. But on the other hand, those odd mass nuclei with one neutron or one proton, or one proton or one neutron removed from the closed shell, you can see various excitation modes with low energy, low excitation energies. Okay, those energies and spin parities actually can be understood nicely based on the shell model. So now I will draw a bit about the shell structure to explain how it works to explain these excitation spectra. So let me begin with just naive textbook example. So usually as we learn in this lecture, the density distribution is constant inside atomic nucleus, and it drops suddenly at the surface. So this is the saturation of the density. Okay, and this kind of shape is called Woods-Saxon type density distribution, and the potential looks similar. I mean, the potential has a similar form with density, just inverse. I mean, okay, and you can compare this with the harmonic oscillator potential. So often one may use harmonic oscillator potential. Okay. So I just indicate the difference. So this is harmonic oscillator potential, and this is the so-called Woods-Saxon type potential, nuclear potential. So it shows that it has more attraction as compared to harmonic oscillator at the surface region. Okay, and it makes so in case of harmonic oscillator, you have a positive parity. Okay, this is positive parity state. The first one is S orbital, and the second one is negative parity state with P orbital. And let's say here, so this is positive parity state, but with S and D orbitals, and so on. And in case of harmonic oscillator potential, those states are degenerated. And also those P and S waves are degenerated. I mean, there are substates. For instance, this P shell contains six orbitals, 6 states, but those are degenerated. But if we move from harmonic oscillator to the Woods-Saxon potential, then for instance, so it is only few examples, but for instance, this d orbital has larger angular momentum, and because of the centrifugal potential, it is extended outwards. So it has more amplitude at the surface region, and it feels this attractive potential. So it makes the difference. For instance, d orbital will gain energy, and p is also gain energy, something like that. So already in this case, with Wood-Saxon potential, it makes this splitting of energy depending on the angular momentums. And on top of that, what Meyer Jensen introduced was the strong spin-orbit coupling. Let's say LS, so spin-orbit interaction. And this spin-orbit interaction affect, so there are two so J is the total angular momentum, so L plus S. And there are two possible cases for spin. So plus 1/2 and minus 1/2. And we call, where should I, okay. So J upper is L plus 1/2, and J lower is L minus 1/2. So this is the different spin orientations. Okay. And now this spin orbit interaction acts attractive for J upper. So LS spin orbit interaction is what is it? Attractive or repulsive for J upper and J lower. Okay, so it makes okay the difference. So for P wave, P orbital, there are two possibilities. So one is okay, let's just SP D F G H I, and for those symbols, we have orbital angular momentum 0, 1, 2, 3, blah blah blah. Okay. So in case of P orbital, it is L equal 1. So plus minus 1/2 provide P 3/2 and P 1/2. And this is S. And here you have larger spin orbit splitting. Yeah, so this larger the L, it becomes larger splitting, spin orbit splitting. So it provides D3/2 at lower energy, and D5/2 at lower energy, and D3/2 at higher energy, and here it is 1/2. So, and this is S. And now, as I mentioned in the last lecture, so this JZ can take 2J plus 1 states. So minus, let's say minus J plus 1 up to plus J. So here is 2J plus 1 degeneracy in each single particle levels. So now 2J plus 1 will be here 2. So if number indicates the JZ. So 2JZ plus 1 can be occupied in this each orbitals. So this S1 half, you can see 2 times S1 half is 1, and plus 1 means 2. So in this way, just you can count those numbers and you can find easily 6, 4, 10, 20, and so on. So this already explains the emergence of those magic numbers, yeah, to H20. And actually, from the next negative parity state, we have the spin orbit splitting for the F orbital. And here is the next F7 half coming from the upper shell, and it has 8, it can contain 8 states, and it explains the next magic number 28, and so on. Okay. So in this way, so this is the case of spherical nucleus, but Woods-Saxon potential plus strong spin orbit coupling can explain those magic numbers. If you have questions, you can share.
2 and 4, where is the 8 coming?
This?
Yeah, the NP, it's 8, but
This?
yeah. 4,
So this is 4 and this is 2. So here you have 6
6.
and here you have 2.
Total,
So in total, yeah. So in this way you can count the number of states that can fill up to certain energy, and you can find magic numbers at the shell closure. Okay, so this is just a preparation. So now let me try to explain those excitation spectra. So I will guess this. But yeah, but this is just a simple rule to count what is next. So if you get familiar with this, you can easily do that. So for instance, the magic, let's start with magic number 50. So magic number 50 is made by a G9 half coming from upper positive parity state. So here I expect the plus parity state, positive parity state. So here should be the J lower. So the partner of G9 half. So it will be G7 half. And there are positive parity states below G. Okay. So S and D. So I may write down in this way. So D5 half and again D3 half and S1 half. But there is a so-called intruder state. Always, it is intruder. I mean, coming from next shell. So next shell it has negative parity, and next largest negative parity orbital will be next to G, and it will be H. So here there should be some intruder state with negative parity and J upper. So it will be H11 half. And yeah, the figure is not nice. So anyway, so here should be the partner H9 half. And here we expect the negative parity state. So now, okay. So I should write the number probably here. Okay, so here we have up to G9 half orbital, we have 50 nucleons. And on top of that, we have, these positive energy shells, positive parity shells. And you can count again, 6, 8, 12, 4, 2. Those are 2J plus 1. And it should be 10, 10, 20, 32. So it explains 32 plus 50, and you have 82. Okay. So now we are coming to the shell of 82, around 82. So as I mentioned here, we can expect the minus negative parity orbitals. And okay, below H, so PF orbital should be there. So F7 half, F5 half, and P3 half, and P1 half. And also, again, the next intruder. So the intruder will be positive parity, and next to H, it means I. So I13 half orbital should coming from the upper shell. It forms positive parity state in the negative parity shells. Okay, now we can again count the numbers. So it should provide us 6, 4, 2, 10, 20, 30, 44. So 44 plus 82 will be 126. So we have 126 here. Okay, so now, so let's start with bismuth 209, for instance. So bismuth 209 has neutron number 126, same as lead 208, but we have one proton added to the closed 82. So we have one proton added to the closed shell 82. So let's put here. So the lead 208 has ground state spin parity 0 plus. So the bismuth 209 should have spin parity of the last occupied proton. It is H9 half, so 9 half minus, because H is a negative parity state. So H9 half minus, 9 half minus here. So it explains the spin parity of ground state of bismuth 209. And now, so as a first excited state of bismuth 209, we can consider just a particle hole excitation from this last occupied orbital to next unoccupied orbital here. So in such a case, the first excited state of bismuth 209 should have negative parity and spin 7 half. So 7 half minus. And you can see this is the experimental data, and here 7 half minus. Okay. And again, as a next excited state, you may consider, okay, so let me put this last occupied proton to next level, this intruder state. And this state is the intruder, and it has positive parity state, positive parity. And the spin is 13 half. So there should be 13 half plus state at the low lying state of bismuth 209. And indeed, you can see here 13 half plus. in this excitation spectrum. So, okay, in this way, the odd mass nuclei with one additional proton or one additional neutron on top of the closed shell has excitation spectra which can be understood from the shell model, like picture. And just to mention, also, for instance, in case of Thallium-217 here, you have 81 protons. So it is somehow different. But in case of, so in this case, you can regard it as one whole state, one whole. So you have occupied, fully occupied closed shell of 82, but we have one hole. So one particle, one proton is missing in the 82 shell. So in such a case, what you expect is spin parity of Thallium-207 should be determined by the last unoccupied hole state. So it will be 1/2 plus. Yeah, indeed it is 1/2 plus. And as an excited state, you can consider to making different hole in the below. So you can feel, so it is kind of excitation from D3 half to S1 half, making fully occupied S1 half of that, but here you have one whole state. So it will be D3 half, so 3 half plus. And you can find here, so D3 half and 3 half plus in this low lying state. And let's see one more. So this is just an example. So as a next possibility, you may consider to excite from this H11 half or to this S1 half actually. So again, you can expect spin parity of this nucleus to be 11 half minus, because H is the intruder state coming from negative parity orbitals. Okay, so this is the intruder. So it has negative parity and 11 half spin. And you can actually see here is 11 half minus in the excitation spectra of Thallium-207. Okay, so you can continue this kind of game to see the correspondence between the shell model picture and the experimental excitation spectrum. So the message is the shell model works pretty well, as you can see here, to explain low-lying excitation spectra of odd mass nuclei near the closed shell. Okay. So, but this is not a collective excitation. It is just a one particle, one hole, simple one particle, one hole to excite the nucleus. So now, let me move on further. Okay. So, however, so there are excited states which cannot be explained simply by this single particle excitations in the shell model picture. So there are some excited states that cannot explain simply using these kind of excitation. And it is a collective excitation, what we call collective excitation. Okay. So let me put one example here. Okay, here I show this kind of single particle energy levels of light nucleus, oxygen 16. Okay. So red colors, red lines shows the neutron single particle levels, and this green lines show the proton single particle levels. And because of the Coulomb potential, the protons levels shifted upwards a bit. So this is a single particle energy. Okay. So you can see, so those thick lines corresponds to occupied state. So you have 8 neutrons and 8 protons, and those form a closed shell. So 8 is magic number. So thinking similarly as before, you may expect as a first excitation energy, you need about 10 MeV or 9 or 8 MeV. I mean, to excite last occupied neutron or proton to the next shell, you need such excitation energy. Okay, so simply thinking about one particle, one force excitation, you need 10 MeV, more or less, to excite this oxygen 16. And this is experimental data taken from this web page. So it shows, several, okay, so this is the ground state, 0 plus, and there are excited states. And those lines indicate some decay modes, gamma rays. And as you can see here, there are some states with 6 MeV or 7 MeV. So there are at least 4 states, low-lying excited states at around 6 or 7 MeV. So it cannot simply explain this one particle excitation. Okay, so what is it? What are those excited states? And also, there are, okay, so this is, again, oxygen 16. And this figure shows a photoabsorption cross-section. So photoabsorption means, so you can bombard, I mean, you can use some projectile with heavy nucleus, for instance, with highly charged, I mean, lead-208 or so. And you can excite nucleus. So this indicates already some idea of collective excitation. So for instance, this shaded circle may represent the proton density, and this is neutron. And you may, okay, so this is lead-208. And coming through, I mean, close to this nucleus, then this Coulomb interaction, I mean, Coulomb repulsion shifts the proton density distribution, and neutron distribution remains. And you have some kind of shift of density distributions. And this is related to such hot absorption. And it shows hot absorption, so cross-section as a function of excitation energy. And there are some peaks at low-lying states. It corresponds to some particle excitation, excitations. And you can find some peculiar huge peak above 22 MeV or so. It is the so-called giant resonance. So when you excite this oxygen 16 nucleus by some Coulomb repulsion, Coulomb field, you have some kind of resonating huge excitation modes, photoabsorption, huge photoabsorption around this excitation energy. Okay. And this is related to the collective excitation, as indicated already here. Okay. So now, let me explain how to describe such excitation modes based on, mean field theory. So we will build the theory for excited states on top of the Hartree-Fock theory. So now, in the following, I do not distinguish DFT and Hartree-Fock. It is closely related. Just you can keep in mind, but we just say it is a Hartree-Fock theory. And the first one is the so-called Tamm-Dancoff approximation, TDA. And those are the guys, Tamm and Dancoff, and both are great physicists, actually. So Tamm received actually the Nobel Prize in physics in 1958 because of his contribution to find and interpret the Cherenkov effect. And Dancoff was nearly getting the Nobel Prize for formulating the QED, quantum electrodynamics, but there were some errors. And actually, Kimonaga corrected those errors and showed that Dancoff's theory works. Okay, so both are great physicists that introduced this TDA, Tamm-Dancoff approximation. Okay, so now, yeah, I will explain. So this is just a preparation, but this is, let's see. This is, yeah, that's just a preparation. So Hartree-Fock theory in second quantization. So actually this will be an assignment. Okay, so yeah, those are just definitions. So Hamiltonian is usual, yeah, generic two-body, one-body and two-body Hamiltonian in the second quantization form. And the Hartree-Fock state is a Slater determinant, but can be expressed as a product of creation operators. You can see that, for instance, because of the fermionic character of this creation operator, if you create a particle at the same state, it will be zero. And if you interchange two operators, then you have negative sign. So actually, this form of wave function satisfies the condition of Slater determinant. So this is the second quantized form of Slater determinant. And you can take the energy expectation value of this Hamiltonian and with this Hartree-Fock state, and you can get this formula. Okay. And I will explain, I will show this slide later again, but this will be an assignment. This should be number 2. Sorry. Okay. So this, based on the variation principle, starting from this energy expectation value here, you can derive the Hartree-Fock condition. Okay, so this condition. And okay, this will be the assignment. But this result of variation indicates that, so this HMI means M indicates these unoccupied states, M and N. So in the following, I will use this index, Mn for the unoccupied state and Ij for occupied state. And this indicates the particle whole. So M indicates the particle states, unoccupied state, and I indicates the whole state, occupied state. So this particle whole or whole particle component is 0 because of this variational principle. And you can manipulate some equations So this is just maybe I will explain this. No. Yeah, so this indicates particle. Okay, yeah, the particle hole and hole particle. So it has this matrix has this kind of form, and this is a particle hole, and this is hole particle, and this this is particle. Maybe hole particle, particle. But anyway, so it has this kind of structure with, because of this result of variation here, the Hamiltonian matrix has 0 for particle hole and hole particle. These blocks are 0. And using these properties, you can show that this is true. And this indicates by, this equality indicates this commutation relation is 0. H commutes with density matrix. So this is the result of variation based on Hartree-Fock approximation. And actually in the last lecture, I showed similar equation for the HFB, Hartree-Fock, Bogoliubov theory. But in that case, H and law was generalized. Okay, so, and also let me mention that if you diagonalize this Hamiltonian matrix, then as you can see, automatically you have, so if you diagonalize this Hamiltonian matrix, then the diagonal components are non-zero and rest are 0. And then you can automatically ensure that this Hartree-Fock condition is fulfilled. So in practice, you can diagonalize this single particle Hamiltonian to get single particle energies, and then it automatically ensures that whole particle and particle hole components are 0, and it ensures this Hartree-Fock condition, the result of variation. Okay, so this will be an assignment. Okay, and I will just use this Hartree-Fock state written here and try to develop the theory for the excited states. Okay, so the Tamm-Dancoff approximation. So what is this? So this is the main idea. What is the Tamm-Dancoff approximation? Okay, so in Tamm-Dancoff approximation, TDA, we seek for solutions for excited states, which are approximated by a superposition of one particle, one hole excitations. Okay, so I explained that low-lying spectra with single one particle, one hole configuration. But now we consider some superposition of various one particle, one hole excitations. So I creates a hole and M creates the particle. And this C is a expansion coefficient. So we will determine this coefficient through the variation condition. Okay, so this Hartree-Fock is just this Slater determinant, and this excited state must be orthogonal to this ground state, Hartree-Fock state. Now, so we will derive the variational equation. So here again, So as usual, we take the expectation value, energy expectation value of Hamiltonian H. But here I just put the prime here, H prime. It means just we measure the energy from the ground state. Yeah. So energy of Hartree-Fock state. So this is the shift of energy. I mean, to see excitation energy. So this is just the energy expectation value. And the rest, okay, this second term is to ensure the orthonormal relation for the excited state. Okay. And we just request this C star, CMI new star, to be as a variation parameter and request this variation condition. Okay. So as I mentioned, what we should do is to perform this variation. To begin with, I will just rewrite this equation a bit. Okay, so here I just put the definition of this new the excited state. So this is the superposition of one part one whole excitations, new. And I just put it here, as you can see. And then, okay, so now I will rewrite this equation. So the second equation is the same. So you can forget about this. So this is the same here and here. And now, okay, so I just put this plus and minus the same term. So I just added the zero, the same to, so this is just a manipulation of this equation. And then, so here I just removed, I mean, from H prime, I just put this minus H Hartree-Fock, the energy shift I mentioned before. So now, this by operating this Hamiltonian to the Hartree-Fock state, you can get EHF, the energy of the Hartree-Fock state. So this energy shift and this term is cancelling out. So this is plus and minus, and this H hat will be H Hartree-Fock. So this will be vanishing. Okay, and the rest is here. And if you look at carefully, you can write this equation by commutation relation, H and A dagger A. And here, the second term, you can use the condition and properties of this creation and annihilation operators. And what you find is these delta functions, Kronecker deltas. And this is a result. So this variation equation leads to this condition. Okay. So the coefficient C must satisfy this condition. So this is a variation equation. But still, this left-hand side contains A dagger and A. So it is not visible how to solve this equation. So what need to do for now is to to calculate this left-hand side to be more easier form. Okay. And as you can see, the tasks will be to calculate this commutation relation, this H and A dagger A, and also this rest of the equation. Okay. And I will just follow what will be the results. So, but those calculations are very similar to what we learned from the last lecture. So, for instance, this is the case of kinetic term. So H contains the kinetic and interaction term, and this is the one-body kinetic term. So this is, okay, so this is the kinetic energy of delta. So A dagger A is sitting here. So this first to A dagger A alpha, A beta, and this last two operators are coming from this kinetic energy operators. And then you can again try, what you should try is to operate this, for instance, Hj. This annihilation, all right? What you should, so here we are trying to reduce number of operators. So what you should try here is to make it a normal order. So all the A dagger should be on the left-hand side, and all A annihilation operators should be on the right-hand side. So now we move those operators, and what we use is again this anti-commutation relations. And if you work carefully, you will get this kind of equation. So you can follow later maybe by looking at these slides. This is just using this relation for the exchanging annihilation operators. So as I mentioned, so here at the beginning, you had 4 operators, but now after this commutation, anti-commutation relations, you have 2 operators because we used this Kronecker delta to reduce the number of operators. So here you have only two operators. And you can repeat this calculation, and this is just a straightforward algebra. Okay, and I skip this, and you will get this equation. And again, at the beginning, for this two-body term, you had 6 operators, but in the end, because of one interchange of annihilation operators, you have 4 operators. So you can, in this way, reduce number of operators a bit. Of course, you don't have to do that, but it will make calculation complex. So it is better to reduce the number of operators before. Okay. So now what we do is this equation, calculation of this term, which was on the left-hand side of this variation condition. So now we put the results of calculation that I presented in the previous slide. So this kinetic term will be something like this. And then again, what you do is this, moving this annihilation operator here to the right, and calculate those terms. And you can find that those 2 terms will be vanishing. And also you can use this Kronecker delta. And this is the result. Okay, so now, as you can see, by taking this expectation value between Hartree-Fock states, you can finally eliminate the creation and annihilation operators. So we just used this condition. So annihilation of whole state is 0 because they are empty. And creation of annihilation of particle state will be 0 because of empty levels. And for the whole state, since there are already occupied states, the creation of the whole state will be 0. So you can just use this relation to eliminate the creation and annihilation operators. And this is the result. Okay, and again, you can repeat these kind of calculations. Yeah, it is a bit lengthy, but straightforward. So you can repeat in a similar way and get this result. Okay, so here is the summary. The point is the following. So as I mentioned, so this equation is a result of variation. So we assumed that the excited state nu is written as the superposition of particle Hall excitations and took a variation with respect to this coefficient C star. And this we got this equation. And here we have derived what will be this term, this left-hand side. And now we put those results into this left-hand side. And by looking at carefully those coefficients, see, you can summarize, put into the parentheses those terms here. And if you remember, this was derived from the Hartree-Fock theory. So if we assume the state will be theta determinant and take a variation, what we got is this Hamiltonian matrix will be the particle Hall or whole particle components of Hamiltonian matrix will be 0. And this actually, those red colored equations corresponds to the Hamiltonian matrix. And we can assume that the Hartree-Fock state diagonalize the Hamiltonian matrix with eigenvalues, which are the single particle energies. Here I denote it as epsilon, and with Kronecker data because of this diagonal components. And it makes equation much simpler. So this is the final result. Okay, so here you have the difference between whole state and particle state. So this will be the excitation energy from one state to the other. And here V bar corresponds to the that was okay. Let me in the Hamiltonian. That was in the Hamiltonian, and where is it? Just a normal here. So that was normal matrix elements for the for the two-body interaction. And bar means it is anti-symmetrized, and so it means if we interchange the indexes, it will generate the negative sign. But anyway, this V bar is associated with this two-body interaction. So let me go back to the slides. So okay, so here you have this excitation energy, and in addition to that, you have this interaction matrix elements. And okay, so the coefficient C must fulfill this equation. And in such a way, we can determine the coefficient C, and we can derive what will be the excited states described by nu, which is a superposition of particle Hall excitations. And this C describes the amplitude, kind of amplitude of which excitation modes, particle Hall excitation contribute the most. Okay, so let's see what is the meaning of Tamm-Dancoff approximation. So this is the TDA equation that we have derived so far. And to see the meaning, let's assume, or let's simplify this equation. So here is the assumption. So we assume that the interaction matrix element here, V bar, has a separable form, the so-called separable form. So lambda is denotes some strength of interaction. And here you have D star. So this Mi and Mj are separable. Okay, so this is a simplification, but with this simplification, the meaning of equation will be more clear. Okay. And this kind of approximation is known as schematic model. So you can find in the textbook this kind of discussion. Okay, so now let me explain what is the meaning of collective states in Tamm-Dancoff approximation. So this is the TDA equation, and here you put this separable simplified form for this matrix element. Okay. So this here and here, I just manipulate those terms. So I just move this right-hand side to the left-hand side. No, maybe it's this left-hand side to the right-hand side. Okay. And you have this equation. Okay. And now what we did is, okay, so this green term, we divide whole equation by this green term to move this part to the right-hand side, and we have here. And then we multiply this D star Mi. So both sides is multiplied by D star Mi. And take a summation over M and I. And now, so you looking at carefully, this sigma D star C nu here and sigma D star C nu here are equivalent. So those has different index, but this is the labeling. So index for summation. So both are the same. So to make this equation, to satisfy this equation, this lambda must be cancelled out with this term. So it indicates that this coefficient here must be 1 over lambda. Then we can cancel this, and this equation falls. Okay. So now we can get what will be what should be, how to say, so the solution, this equation gives us a solution for the Tamm-Dancoff approximation. Yeah, and D, here D corresponds to this separable interaction. So this D is related to this interaction, and lambda is also related to the magnitude and the sign of the interaction. And in the denominator, you can see you have excitation energy in U, and also the energy difference between the particle and whole states. Okay. So now let me explain graphically what is the meaning of the solution. Okay. So now I draw the excited states, I mean the energies as a function of excitation energy E nu. And here, yeah, with separable interaction, we could derive this equation. And now I'm drawing the each contribution of this right-hand side. Okay, so so this epsilon1, epsilon2, blah, 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 indicates the energy for the particle Hall excitation. So these epsilon corresponds to the energy difference between Hall state and particle state. And at each particle excitation energy, the denominator is vanishingly small. Then the right-hand side becomes divergently large or small. Okay? So it provides us this kind of behavior. And now we draw the left-hand side. So left-hand side is 1 over lambda. So depending on the strength, lambda, and the sign of the lambda, we can get this, we can draw this horizontal lines like this or like this. So green line corresponds to the positive lambda and red line corresponds to negative lambda. Okay. And the solution is when both sides are equal. So the crossing points are related to the solution of this Tamm-Dancoff equation. Okay, so you can find those cross points between 1 over lambda and these blue lines. Those are solutions related to the solutions. And as you can see, you have those cross sections, I mean cross points, close to particle excitation energies. So those are just a particle excitation that I naively explained in the beginning of this lecture. So this is just a particle excitation. But other than that, we have some states with different excitation energies. One is here and the other is here. So for instance, for positive lambda, we have this energy and it is related to actually the collective state. And this collective state emerges at high excitation energy. So when this interaction, two-body interaction is repulsive, then there is a state with very high excitation energy, which is related to the collective state. On the other hand, when you have attractive interaction, so negative lambda, this Tamm-Dancoff equation indicates that there should be some low-lying collective states at lower excitation energy, which is actually lower than this first excited energy of particle Hall excitation. So there is a state which can emerge below this first particle Hall excitation energy. Okay, so okay. Now, so let me explain a bit more. So what is this collective energy? So now to explain this, we consider more simplified case where all states are degenerated. So I showed many possible excitations, but now I assume that those particle excitations are degenerated. So it may be may correspond to some excitation from one state to upper level. So there are several states here, and we consider excitation to this single state. So this is a simplified assumption. So here we can put epsilon mi to be some single value epsilon. Okay, so this energy is epsilon. And now, so it's where is so those will be epsilon, and yeah, you can put EMEI. This difference will be epsilon, and yeah, you can just regard this E nu as equal collective energy. Yeah, and you will get this equation. And now, so in such a case, yeah, the situation is similar. So depending on the sign of the interaction, here, you have collective state at higher energy or lower energy. And in this case, yeah, so in this case, how to say, so yeah, so in this case, what was this? So yeah, all states, so yeah, these excitations, single particle excitations contribute equally to develop this collective energy. And one can write down these coefficients is equal, and this coefficient will be described this D coefficient. But with this coefficient, all the particle form excitations contribute equally or coherently. So this is nothing but the collective, yeah, so this coming from this normalization condition. So this collective state has this normalization factor with this kind of superposition. And now, yeah, this is just additional information that this is kind of transition probability, and D, okay, D is some kind of external operator that excites the ground state or Hartree-Fock state to the collective excited state, new call here. And this transition probability or amplitude of excitation can be written in this way. And you can see that this excitation, amplitude of excitation, can be written as the summation of D, D squared. And yeah, so this is related to this energy of collective excitations. And one can show that in this particular case, with fully degenerate case, this exhausts 100% of the sum rule. So sum rule means this excitation is the only excitation. So this is very peculiar case, but in such a case, all the particle form excitations contribute coherently, and it enhances the transition probability in such a case. So in any way, so the bottom line message is there is the so-called collective excitations, and in this collective excitation, many particle excitations are contributing equally or coherently, and it makes the amplitude transition probability higher. And this is related to the emergence of the giant resonances and also the low-lying excited states that I mentioned in the beginning of this lecture. The oxygen 16 has lower excitation modes below the simple one particle, one hole excitation. So anyway, yeah, this is the properties of Tamm-Dancoff equations, and that gives us some idea of collective states. And now, in the rest of 20 minutes or so, I will briefly explain how to improve the description. So actually, in this case, we used the Hartree-Fock state as a ground state, and we just think about the particle superposition of particle excitation on top of this Hartree-Fock state. But actually, yeah, this is not perfect. I mean, this is a simple approximation. And more sophisticated description can be obtained with the so-called random phase approximation, RPA, which introduce kind of ground state correlations or some modification of the ground state through this particle correlation. So now let me explain what is the RPA and how to derive it, and what is the relation between TDA and RPA. So to explain this, let me introduce another derivation of Tamm-Dancoff approximation. So this is the so-called equation of motion method. So far, I just used the relation of anti-commutation relations, and I just simply take the expectation value and variation principle. But now I like to derive that equation, the same equation, with somewhat different way. So now, in this equation of motion method, we define some kind of creation and annihilation operators for the collective states. So the starting point is somewhat different. So we consider kind of annihilation and creation operator for the collective states. So it means that, okay, so this Q dagger is a creation operator. And by operating this Q dagger onto the vacuum state, we have this collective states nu. And it satisfies this equation. So E nu is the correct excitation energy. And we optimize this operator through the variation principle. So what we do is similar to the variation condition to derive any theory like Hartree-Fock or BCS or Tamm-Dancoff equations, but we consider variation with respect to this operator Q. And the derivation is quite similar, actually, similar to the Tamm-Dancoff case. So now here I just put the definition of nu, this state, here and here. So Brown ket state are replaced with this definition, and take the variation with respect to this operator. So this is somewhat different, but this Q hat is somehow becomes a delta Q. So now, again, this is the same way this HQ dagger can be written as this commutation relation plus the ground state energy. And this latter part is similar. We can calculate, we can get this commutation relation because by multiplying Q dagger to the glass state, it will be 0. And then we have this equation. So now it is the same as before. So this first term is sitting over here, and the rest is on the right hand side. So this is, variation condition derived with this operator. So up to now, we do not specify what is Q dagger. So this is the general equation. And we can compute this doubly commutation relation again, and we just use the relation here. And eventually, what you have is this equation. So, so now we can derive the TDA, Tamm-Dancoff equation, by specifying this operator Q dagger to be the A dagger A, superposition of A dagger A. Okay, so you can put this A dagger A here and here, and then here. And taking Hartree-Fock state means this vacuum state is replaced with Hartree-Fock state. Then it will end up with the same equation that we have derived before. Okay, so this is the so-called equation of motion method to define some operator for the collective, or some operator, in this case, that describes the collective state, and take the variation. And later, we specify what is the state and what is the actual form of this operator. Okay, now let us derive what is a RPA. So in this case, we change the operator and vacuum state. So now, this is the phonon creation operator in random phase approximation, RPA. So Q dagger has this A dagger A and A dagger A, another A dagger here. So looking at carefully, the first term is the same. So AI is the annihilation operator of occupied state, and AM dagger corresponds to the creation to the unoccupied state. So this is the particle Hall excitation, superposition of particle Hall excitation. So this is up to here, it is the same as Tamm-Dancoff approximation. But in addition to that, we have additional term here. So this is kind of a backward amplitude. So as you can see, this corresponds to annihilation of the particle state and creation of the whole state. So this means, so if you operate this onto the Hartree-Fock state, it is 0. But after excitation, particle excitation, you may have some particle states on top of the Hartree-Fock ground state and the whole state below the, Hartree-Fock ground state. So then you can have such an excitation by creating, by annihilating a particle state and creating a whole state, or it is a backward excitation or de-excitation of particle state to the whole state. So in this way, somehow this phonon creation operator is generalized in RPA. And in this equation of motion method, what we require is this Hono vacuum. So Q of the operation Q becomes 0. Okay, so this is RPA state, not the Hartree-Fock state. So this is one point. So in case of Tamm-Dancoff approximation, we use Hartree-Fock state as a vacuum, Hono vacuum, or ground state. But in this case, we introduce somewhat different states, which is different from the Hartree-Fock state. So now, so again, what we do is following variational calculation. So this is what are the difference? Yeah, so here, yeah, we take variation with respect to not only x, this forward amplitude, but also this y, this backward amplitude. And it will give you these two equations. Yeah. And but yeah, because of this different A daga A, as you can see, so this order is different. And there are two different coefficients. You can derive these two equations, which is somehow with different indexes. Yeah, you can see here, IM and MI. So now, in RPA, we introduce the so-called quasi-boson approximation to calculate this expectation value of commutation relation with RPA states. So it means, yeah, what does it mean is, so in case of these four creation and annihilation operators, you will have this Kronecker delta and some additional terms with two annihilation operators and yeah, A daga and A daga A. And in quasi-boson approximation, actually we neglect those two additional terms. So what meaning is, yeah. So for instance, this corresponds to some de-excitation. So creation of a whole state and annihilation, yeah, not a de-excitation, but some excitation between the whole state. So creation of the whole state, but annihilation of whole state. So this term contains both the whole states, and this amplitude must be small. I mean, it's to have this excitation, we originally have the hole in this state, and it is proportional to the number of holes in the RPA state. And this number should be small, not so large. And also, this is similar. So this is the annihilation of the particle state and the creation of the particle state. So it is some kind of, yeah, or annihilation of already occupied particle state and creation of some other particle state. And also this should be proportional to the number of particle state, and those must be small. So based on this kind of argument, in RPA, we neglect those additional terms, and in the end, what we have is this expectation value, the sandwich of this commutation relation is just Kronecker deltas. And it is very similar to what we have in, not similar. It is equal to what we have the equation for Hartree-Fock state. So if you take this expectation value by Hartree-Fock state, it will be just a Kronecker deltas. And in RPA, with RPA state, you can calculate in this way, but neglecting these additional terms, you can assume that this expectation value becomes the same as Hartree-Fock state. So it makes the equation much simpler, and it makes a similarity with Hartree-Fock states. Okay, so this is the so-called K-psi boson approximation, and so this approximation, the reason why it is called K-psi boson approximation is, so if you look at this commutation relation and this result, and forget about this expectation value, then this looks like the commutation relation of bosonic operator. So you can regard A daga A as a bosonic operator, then it provides you this Kronecker delta. And this K-psi boson approximation assumes that this bosonic commutation relation is satisfied at the expectation value, level of expectation value in the RPA state. Okay, then this was the approximation, and then you can use that K-psi boson approximation to calculate this A daga A and A daga A sandwiched with RPA states, and after some calculation, you can get this RPA equation. Okay, so again, so this first equation was derived by variation with respect to x, and second equation was derived with respect to the variation with respect to y, backward amplitude, and from those equations, you can derive these two equations. And here I define some matrix A and B, which is related to actually this commutation relations, and you can calculate it in this way. So A term corresponds to the same as Tamm-Dancoff approximation that you saw in the first part of this lecture, and B corresponds to the this matrix elements in here. And as written here, this this definition of A corresponds to what was written in the left-hand side of the TDA equation. And you can write this equation with matrix representation. So you can see that this A, B contains two indexes, Mi and Mj, and here this X and Y contains the index Nj here. So you can write this equation with matrix like this. And this is well-known RPA equation. So by solving this equation, you can determine the backward and forward amplitudes X and Y. And by having X and Y amplitudes, you can get what is the RPA phonon operator, and also what will be the excitation energy, and so on. So this is the RPA equation. And in the next lecture, I will explain some kind of time-dependent Hartree-Fock. This is a time-dependent extension of Hartree-Fock theory that can describe many dynamic phenomena, including highly nonlinear excitation modes. But in the next lecture, I will also derive this RPA equation from the linear amplitude, small amplitude method, and small amplitude limit of TDHF. So I will explain a bit in the next lecture. Okay, so now let's see again the graphical interpretation of this RPA equation. So again, we assume the separable form of the interaction to simplify the conclusion. But now, again, I draw, here is the excitation energy in U. And okay, so this is the RPA equation with separable interaction. So now V bar is lambda times DD star. So we use separable interaction. And okay, so this is how it looks. So these blue lines corresponds to the right-hand side, okay? So again, this blue line, this dashed line, okay, corresponds to the particle Hall excitation energy. So when this excitation energy becomes, close to the particle excitation energies, this right-hand side is diverging. And now, you can draw the left-hand side, this 1 over lambda, and it depends on the sign of the lambda and the amplitude of the lambda. So, and those are cross points and related to the solution of these RPA equations. Okay, and then the point is, for instance, for the positive, repulsive interaction, in addition to those states close to the particle Hall excitation energies, you have some collective excitation, collective states with higher excitation. So this is similar to the Tamm-Dancoff approximation. And okay, so and here I draw E0. E0 is the ground state energy. So we should focus on these positive energy states. I mean the E nu larger than E0. Okay, so these are excitation modes. And this is similar to Tamm-Dancoff case. On the other side, for attractive interaction, we have this solution here. So it is smaller than the smallest particle Hall excitation energy. So this is also similar to the Tamm-Dancoff approximation. But you can see some difference. So the shape of this curve is not going to this way, but going upward in this way. So it indicates that there is some region where we do not have some cross point of the collective states. Okay, so when interaction is negatively large, so 1 over lambda is negative and small, so lambda is larger and larger, then you will have a region where you miss the collective states here. Okay, and this is related to some instability. So when you have some strong attractive interaction, then there is no collective state, collective solution. It means E nu, the correct excitation energy, E nu becomes imaginary. So not the real value, but the imaginary solution you will have. Okay. And it indicates that there is some better ground state other than Hartree-Fock state. So it indicates that because of some residual interaction, which has some attractive interaction, the ground state that you may prepare is not the true ground state. Yeah, it indicates that there exists some better ground state with lower energy than Hartree-Fock state. So this random phase approximation can include some kind of ground state correlations on top of Hartree-Fock state, and also it can be used to have some insight of stability or instability of the Hartree-Fock ground state. Okay, so those are some graphical interpretation of the RPA equation. And now let me briefly summarize this lecture. So in atomic nuclei, there exist various collective excitation modes. So I introduced some kind of photoabsorption. So that was actually out of phase oscillation of neutron and proton densities, the so-called isobector giant dipole resonance. But there are many other collective excitation modes like surface vibrations and rotations and so on. And in Tamm-Dancoff approximation TDA, the ground state is kept to the Hartree-Fock state, and on top of that, we built the excited state as a superposition of one particle, one whole excitations. And we could find the collective state with higher or lower energy, depending on the sign of the interaction, as a coherent superposition of one particle, one whole excitations. And in case of RPA, it is also known as new TDA, new Tamm-Dancoff approximation, which introduced kind of ground state correlations so the ground state is not Hartree-Fock state, but we have RPA state, which includes some correlations. And by adding backward amplitude to the creation operator of Hono operator in the TDA, we could derive RPA equations. Okay, so those are important, basic frameworks to describe the collective excitations in finite nuclei. Okay, so, and this is just the end of my lecture, and I will inform you by T2 Scala, but this is the assignment too. So, starting with this definition of Hamiltonian and Hartree-Fock state, you can try to derive the Hartree-Fock condition, and which provides you this well-known Hartree-Fock condition. And I just set the 1 week for preparation. So please submit until this date and time via T2 Scala. Okay. So if you have questions, please ask.